Okay, so if you've done the move for the base catalyzed conversion of a carbonyl to a hemiacetal or hemiketal, if you haven't done that one, please make sure you do that one before you look at this one here, because it won't make a lot of things will make sense to you. So do the base catalyzed one first. Okay, so for the acid catalyzed conversion, what we're going to do here is we're going to take a ketone or an aldehyde, doesn't matter, and I got a ketone here, acetone, and we're going to react it with an alcohol. And so that could be methanol, could be ethanol, could be propanol, could be isopropanol. And we're doing acid catalyzed chemistry. So we're in the circle on the far hand side here. I'm going to put a plus sign in the circle because we're doing acid catalyzed chemistry. So I better not see any minus charges on anything in this mechanism. Okay. Okay. So we're going to take the ketone. We're going to have it convert into the hemi stage, and then it will continue to react all the way until it makes the full-on ketal, where you when I think about the acetone, right? The acetone you can think about like this. If this is acetone, then we can say this molecule here and this molecule here, regardless of what R is. Could be carbon, could be hydrogens. One could be hydrogen, one could be a carbon, but the oxidation states are the same for the carbonyl carbons here and here. The oxidation states are the same. And so this is really kind of like it's like a hydrolysis type reaction that we're doing this. Or and actually, if we did this with water, we would call it a hydrolysis reaction. That's why we make the hydrate. But we're doing it with the methanol. And so remember, when we had alkenes, we took alkenes and we were taking alkenes and we did methanolysis of an alkene. We added the methanol across the double bond. We're doing the exact same thing here, right? This is not new. We're adding the methanol across the double bond. Now the double bond is not a carbon-carbon double bond; it's a carbon-oxygen double bond, but nonetheless, it's a double bond. So we really have seen all this chemistry before in other molecules. We're just going to change it by making it a ketone instead of for instance, an alkene. So let's do it exactly the way we did before with our alkene chemistry. We'll start off by saying step number one, we will protonate the alkene, in this case, the carbonyl oxygen. It's more nucleophilic, so the best nucleophile goes after the best electrophile. And once we protonate that, we're going to activate the carbonyl. And by activate it, what I mean is we're putting a plus charge on it. Therefore, the electron is going to get pulled out onto it to give it a lone pair of electrons. So I'm going to do the double-headed resonance arrow here so that I can see this is just a resonance contributor. I got a plus charge on the carbon. Okay, now I have, let's say I'll do this with ethanol for this one. So over the arrow here, each of the alcohols is going to be ethanol. So ET and ET. Okay, so now here in the mechanism, I will say, all right, so then I'm going to have ethanol add in. Ethanol is not usually considered a very strong nucleophile, but that's okay because I got a really strong electrophile. So the electrons on the oxygen of the ethanol go best nucleophile after best electrophile, they add in, and that gets me to here. This plus charge, that's a ET ethanol. So there's a plus charge in the oxygen, oxonium ion. You got a proton of that oxygen, you're going to want to get rid of it, so you're going to take a general base, which is really just another molecule of ethanol. Pull off the proton, leave the electrons behind. And now you have the hemiacetal of the ketone you started with, right, or the hemiketal. Now, if we want to continue, and actually, you know what? If you want to stop at the stage, if you want to make the hemi stage here, and that's the product you want, you probably should not do it with acid catalysis. You should do it with base catalysis because that's as far as the base catalysis reaction goes. You can't get it to go any further. But with the acid catalysis, it can go further. And so it can be kind of messy to try to expect the molecule to stop here. It can be really tricky to expect it to stop here because what it is going to probably do is going to be, well, I still have acid around for my catalyst, so I'm going to take that catalyst as electrophile. I'm going to protonate the oxygen here. And that's going to give it to here. And we've done this a gazillion times this year, where the reason we're doing this is because we want to make the O a better leaving group. It doesn't work as an OH, but it does work as an OH2 or H2O. So now I've got this water will drop off. Okay, and so when I lose that water molecule there, then what am I going to get? So I'll go down to the next page. And so what we get there is Actually, let me just copy this first onto the next page, and then we'll have a good starting place. So copy this. And then for the next page, that is where we'll start. Okay, so then we're going to lose water as we come down here. So minus H2O. When the water falls off, it's going to form a nice tri-substituted resonance stabilized carbocation. So let's go ahead and draw the resonance contributor for that. Double-headed arrow. Electrons in the oxygen are going to resonate down to kind of spread out that plus charge. That's going to give me this. And then from either one of these two resonance distributors, you can say we need to add another molecule of ethanol in here. So from either one of these two, because really if they're resonance forms, they really are the same thing. So we'll take another second equivalent of ethanol for our solvent. And we'll have it add in best nucleophile, goes after best electrophile. And that's going to form another carbon-oxygen bond down here with an ethyl and a proton with a plus charge in the oxygen. So pK of that proton is very acidic, so we'll take another general base, which is another ethanol molecule. We'll pull off the proton. We'll have the electrons going back towards the oxygen, and that gives me, for a final product, the diethyl acetal of acetone. So when I look at this, I can say, if I want to retrosynthetically look at this, I'm going to say, well, what this is, it's a carbon bonded to two oxygens. Another one I know is bonded to oxygens is when it's a double bond instead of two single bonds. Well, this is two single bonds. But if I think about it in terms of two double bonds, I can always spot right away what the starting parent compound was when I look at the hemiacetal or the acetal version of that compound. I just understand that I'm not doing any redox chemistry here. And so I'm just going to say, okay, so I've got, two carbon oxygen bonds there. I've got two here. It could be the dimethyl acetal. It could be the diethyl acetal. It doesn't matter what the alcohols are to be able to do this. So the mechanism for this one is twice as long as the mechanism for the base catalyzed one, and it's twice as long as the mechanism to get to the hemiacetal stage. That makes sense there, because if it's going to get to the halfway stage with half the steps in the mechanism, then the other half will take you home all the way to the full-on diethyl, dimethyl, whatever, acetal. We have two pieces of carbon cabbage. You're making the diether, but it's not an ether, it's an acetal. Okay, and then one of the best acetals you can make, if you think about it, here, if I did this with methanol, I take on two equivalents of methanol. If I do it with ethanol, I take on two equivalents of ethanol. You don't want to do it with like mixtures of methanol, ethanol, because then you get these mixtures of acetals that are, it's really messy. But one of the best acetals to make is this one here. If I want to take any carbonyl, and any carbonyl I take, I react with, and I'll show you the two favorite ones. The two best ones are this one here. That's ethylene glycol. So it's I got both alcohols on the one molecule, and I can do acid catalysis, or I can take an aldehyde or a ketone, and I can react it with propylene glycol and acid catalyst. And by going through the exact same steps of the mechanism, I mean, every single step is exactly the same as we looked at here in this one here. If I follow every single step of that mechanism exactly the same, what I will make is this. For the top reaction, I will make that compound, and for the bottom reaction, I will make that compound. And those are great compounds to make because, as we've learned from going all the way back to the very, very early weeks of fall quarter, we know that one of the major differences here is we have a 5-member ring here and a 6-member ring here. And while the 6-member ring is going to be slightly better than the 5, they're both really, really great stable ring sizes to make in organic chemistry. And this one here actually will adopt a chair conformation. If you use your model, can look at it, it does adopt a true chair conformation in that 6-member ring there for that. And so this you should add to your protecting groups each, because these are protecting groups of carbonyls. If you have a carbonyl and you're trying to do chemistry around the carbonyl and you don't want to touch the carbonyl, but you've got any kind of nucleophilic chemistry going on, even like a weak nucleophile nearby, then you better protect the carbonyl and hide it. And this is the way you hide carbonyls. You make acetals to hide them, because now these are sp3 hybridized bonds, not sp2. So therefore, it's going to be pretty stable to a lot of conditions you might be doing where you're adding nucleophiles elsewhere in your molecule and you don't want to mess up the carbonyl. So you can think of these as protecting groups, but they are simply, so protecting group. So they're simply coming from the ethylene glycol and the propylene glycol. They're making cyclic acetals of the carbonyl, and those are great. Probably the most popular protecting groups for carbonyls are the cyclic acetals. Okay, so that's going to be the acid catalyzed conversion of carbonyls to acetals.